Hey everybody, welcome to CENG 176. I am your guest lecturer for today, Dr. Drews. So if you are still here from the previous one, this is going to be a repeat of what we did earlier. But for those of you just joining us, welcome. Good to have you here. Hopefully we are meeting again. I would assume that we've all had a class together at this point. I'm not sure how you could have gotten through 113 and somehow sidestepped me, but I suppose that it's possible. I wish we could be meeting in person. That would be great, but we're going to be able to knock this out pretty well over Twitch. So I think this should generally go pretty painlessly. I am going to switch chat over to emote only. If you're enrolled in the class, you should have received a Zoom link. And so I am in the Zoom link right now. I'll throw a little message over there. So if you do have questions, you can put them over in the Zoom link or the Zoom chat, and I will be able to see them over there. But otherwise, we're going to emote only over here. And I'm just going to close the chat window on Twitch, so I won't see anything that's over there. I would generally suggest that you do the same, because we've only got about 80 minutes, and we'll have to move through this fairly quickly. What we're going to talk about is an introduction to LaTeX, which is another type of typesetting software. So it's a little bit different from Word. At the end of the day, the final product is the same thing, right? It's a document that you send around that other people can read or print out or something like that. But the method by which LaTeX generates its document is kind of different from Word or Google Docs or whatever it is that you want to do. First, the pronunciation LaTeX, the core is that tech, the T-E-X. You can, LaTeX or LaTeX is fine, as long as you get that kind of like K sound on the tech. That's all I would ask that you do. It's kind of like when you hear somebody say tortilla or chablis. It's like, no, it's tortilla. Like, I know what you meant, right? You said tortilla. I know what you mean. There's not anything wrong with it, but, you know, that's not how it's pronounced. It's pronounced tech. That was the sort of root program, was just tech. And it was originally written when Donald Knuth, which is, you know, kind of the guy who wrote the Bible of C programming, the art of computer programming. He was trying to get a book published, and they had just switched from like physical galley proofs to digital printing press. And he was pissed off about the way that his galley came out. Like, it didn't look good. So, you know, he did what every reasonable person would do, and he wrote his entirely own new, unique typesetting platform, which of course we can all do. Tech by itself was, I mean, it was good for Donald Knuth. Not a lot of people used it because it was a little bit complicated. But later on, Leslie Lamport came along and sort of wrapped a lot of the basic functions in newer, easier to use macros. And that's where we got LaTeX from. So presumably the LA in LaTeX comes from Lamport. He abbreviated his first two on there. LaTeX is free and open source. So unlike Word, you don't have to pay for it. In this class, you'll be using Overleaf, which is sort of a mixture of the two. The core LaTeX features on Overleaf are free. You can personally use LaTeX for your own uses for free. But if you want to share your documents with other people so that they can edit them, that's where you need a subscription. The department, though, has already paid for that subscription, so you don't need to pay for that subscription. If you don't have your subscription yet, talk with Dr. Opakowitz, and he can get you added to our group. So it is still free at this point, but even if you don't like Overleaf, you can always download your own version of a LaTeX editor. It's sort of like C or C++ in that sense. Nobody owns the language, but there are different editors that you can get, and you have to pay for some of those editors, and some of those editors are free. That's kind of where LaTeX is. Most of the editors for LaTeX are free. Some of them that have certain features like Overleaf, where you can have simultaneous people editing them at the same time, and it's all stored on the cloud, that you have to pay for, unless you're just using it for yourself, in which case it's free. The key idea of LaTeX versus Word is the manner in which you interact with it. And by example, think of the way that you would create a plot in Excel versus the way that you would create a plot in MATLAB. In Excel, once you've got that plot set up the way that you want, if you want to change its appearance, you kind of have to navigate your way through a GUI, right? If you want the line to be, blue and a little bit thicker, you click on the line and then you find the blue button and you click on blue, and then you find the button that says make the width a little bit more and you set the width that you want. It kind of reminds me of finger painting, right? Because it's basically all done with a left click, and you're just kind of dragging your finger around the screen and finger painting until it looks nice. There's nothing wrong with that. The other option is what you would have experienced in a program like MATLAB, where if you want, the line to be blue, you would say the quote and then a B and then a quote, right? It's a way of communicating to the code, I would like you to make this blue. If you want the line to be thicker, you might say like line width and then set it equal to 10 or something like that. The difference in those two editors, the first one, the one that's like Word and Excel, is called what you see is what you get. So the way the document appears on the page, that is more or less exactly what it's going to look like when it prints out. Versus the MATLAB version and the LaTeX version is called what you want is what you get. And so you provide codes to a language that processes that code in order to give you whatever it is you asked for. And that's where LaTeX is. The structure of LaTeX is really similar to the web. So the web is based on HTML and CSS in general terms. HTML is usually where the content goes. CSS is what makes all of the websites look different, right? But when you're within a particular website, they all have a kind of similar feel to them, right? They use the same set of colors, the same typefaces, the same font sizes. That's all set by CSS code. And then the content is, some of the things are set by HTML in terms of what they look like. But that's very similar to what we're going to see with LaTeX. There's a chunk of LaTeX in a document that's designed to say, for the most part, this is what your document looks like. This is, the spacing between words. This is the typeface. This is the font size that I want, margins and all that kind of stuff. That's set in one part of the document. And then the rest of the document is content. For the most part, we've already set the way the documents will look in 176 for you. We've already established that set of guidelines, so you don't have to set any of that. In fact, I'd ask that you don't set any of that, because if you mess it up, it's probably going to come back to me and be like, you got to fix this. I'm like, I don't know how. And I'll just say re-download the template so that you can get the fresh template. Nevertheless, we're going to start a LaTeX document from scratch because you may actually find that you like it. You like the way that this looks, and you might want to use it for yourself. The case is where you might want to use LaTeX versus Word. It's like any other platform. It's good at some things and it's not good at other things. It has its use cases. The places where LaTeX shines are definitely within STEM, so science, technology, engineering, and math. It's really good at preparing documents who you expect to be read, or those documents you expect to be read by other people in STEM. So things that include figures and captions and equations and citations and all of that kind of stuff. LaTeX are really good at that, and that's where it finds an enormous amount of its use is in STEM. In fact, I think if you look down at, if you go to the About page on Overleaf somewhere, you'll see a bunch of the people that use it are a bunch of universities because we have to do that kind of writing. The reason it's good at that is because one of the key things LaTeX is good at is if I want a particular document to have a similar feel to another document, that's easy to do on LaTeX, right? Because more or less you just move a preamble from one file to the other, and so you can make lots of documents have a similar feel. For example, if you were in 113 and downloaded some of my PDFs, they all had kind of a similar feel because they were all written in LaTeX. So they started off with like the same header and the same typeface and all of that stuff, and all I had to do was change the content that was underneath. LaTeX also really good at writing very large documents, so mostly textbooks. The majority of textbooks that you've ever picked up have been typeset inside of LaTeX because the ability to refer back to things that happened earlier in the textbook is pretty straightforward on LaTeX, and we're going to see how to do that towards the end of the lecture today. And then the last place that LaTeX is really good at is if you need one of something to look really good. It's kind of hard to put your finger on exactly what it is about LaTeX that makes one document in a PDF look different from Word. But the more you use it, the more you can start to spot like, oh yeah, they made that in Word or they made that in LaTeX or something like that. I'll leave it to you to decide whether you think it looks better or not as a single document. I'm on the side of, yeah, I think it does. But that doesn't mean that Word is not good. So the times where you would use Word instead of LaTeX, by far the biggest one is almost everybody uses Word, right? You can send a Word document to almost anybody. They can open it, they can edit it, and they can send it back to you. And they don't need to know the ideas behind, like, oh, you messed up a closing bracket, and therefore you got an error and the whole thing wouldn't compile. That just doesn't happen in Word, and that makes Word very appealing in that particular sense, right? That's why you'll see Word used an awful lot in industry because they don't often have to typeset the kind of stuff that we do inside of STEM. So it's a different use case between the two. Word's also nice when you just need to like bang out a quick document, right? I just need like a paragraph or a page or something like that. I don't really care about what it looks like. I do know I might have to edit it later. It's nice to just be able to fire open Word and change a couple of things and then send it off to somebody. So they are sort of use cases. It depends on what you want to do. Overleaf, if you dig around in their templates, also has templates for CVs and resumes. So if you're drafting one of those, you can check out the templates for something like that on Overleaf. So those are the big cases. It works really well in STEM, which is mostly where we see it. But it comes at the cost of there is a little bit more of a learning curve, so it's not as widespread. But within STEM, it's pretty darn popular, especially some of its tools, as we'll talk about here in a moment. So let's switch over to Overleaf. Like I said earlier, I assume that you've already got your account made in Overleaf. So you should be greeted with a page that looks something like this, where you have to log in. I'll go ahead and log in here. You may or may not have any projects. LaTeX, there is such a thing as a document in LaTeX, but it is usually organized as a project. The reason being we often have to bring along extra files like figures or data files or code files or something like that that we want to be included inside of our document. And so that's why what you see over here on the left is a button called New Project and not New Document. We usually think of a LaTeX thing as a project and not a document. If you have any previous files, they're all going to be set up in here somewhere. So if you've got one that you want to work on, you can find it in there. We're going to start with a brand new one so that we can kind of build up from scratch what it is we do in a LaTeX document. So I'm going to click on New Project. There are a couple of examples down here. You're more than welcome to poke through them. You can go find the templates. Notice most of them are thinking about STEM, right? Homework assignments, posters, presentations, lab reports, CVs, thesis, academic journal. Overleaf is very much in the STEM space in addition to LaTeX. So if you want to check out some templates, you can look there. But we just want a blank project. So you can name it anything that you want. I'm just going to call it Superfly LaTeX. When you open that, you're going to get a series of windows that looks like this. And so like learning any new piece of software, I just want you to know what you're looking at when you see these windows. This window over here on the left, these are where your files will go. There's always going to be one called main.tech. For the most part, I would suggest you leave main.tech. That's the file that's going to contain, if not all of the content, at least all of the organization of the content. So leave main.tech alone. This window here in the middle, this is your source file. We're actually editing the source file here, so we are viewing this in the editor. This file over here, this is a preview of what we call the compiled document. Compilation in LaTeX is how we go from a source to a final document over here. So if we want to transform our source into a particular document, we compile it. It kind of always starts off as a document, right? We already can see a bit of a document there. And so the button that we use to initiate that compilation process is called Recompile, and that sits up here. The reason it's called re is you always get one first, right? It automatically compiles the first time, so you're just recompiling after that. Try not to get into the habit of hitting recompile every time you add a sentence. I know we're going to do that a lot here over the next 60 minutes or something, but try not to get into that habit. The idea is you put in a fair amount of content and then recompile it later. rather than every few seconds you hit recompile. There is an auto-compile feature, which I don't really recommend because it's more annoying to see changes here and then see a bunch of changes over here, some of which may result in errors, than it is to just leave it and hit recompile every few minutes. There's two ways that you can view the source. Right now, we're highlighted on this green source button here. There's also this rich text option that I'm not going to use. Rich text is this weird sort of uncanny valley somewhere in between code, like what we're used to seeing in like MATLAB and now in LaTeX, and the other part of like Word, right, where you see the bold and the stuff like that. It's somewhere in between, and I don't really like it. You're welcome to use it, but I probably won't be able to help you until you switch back over to the source view, which is what we see here right now. A couple of other things. Eventually, we're going to have to add some files to this document. There's an upload button up here in the top left. We'll come back to that to upload an image a little bit further in class. There is a chat button. So the thing that we're paying for in LaTeX is your ability to chat with other people, in addition to your ability to share the document with other people. The share button is next to the chat button, or near it. The way that the share button works is one person in your team will get the template, they'll create your report document, and then share it out to the rest of your team members, and then you can all edit that document simultaneously. I said before, LaTeX is free and open source. That's the feature that you're paying for in Overleaf that doesn't come with most editors. That, in addition to being stored on the cloud and auto-backing up like a Google Sheet would do. So if you don't need that functionality, you can still use Overleaf for free after the class is over. But if you do need that functionality to share with people, you'll probably have to buy yourself an account. You've already got an account, though, so don't think that you need to go buy an account. If you don't have your account, talk to Dr. Opakowitz. He can help you get set up with that. And then I think the last button that we need is the download button. This button will get the PDF. So when you're ready for your report to be submitted, you're going to have to turn it in with a PDF. That button will download the PDF. It'll look just like any other PDF that you've worked with. So that's the primary interface that we're working with. I'm going to close the file browser because right now we're not worried about the files. We're going to talk about the structure of the code. The other thing that I'm going to do is take everything that's in here and delete it so that we can generate it one at a time. And then last but not least, over here on menu, there are some options down here that can change the way the editor looks. But keep in mind that's changing the editor. It does not have any impact on the compiled document. So for example, if I wanted my editor font size to be 12 or 13 or whatever like that, that's only setting the font size in the editor. Similarly, the font family, there's only 2 font families on there. LaTeX has a lot more than that. You're only setting the font of the editor, not the actual file. So I'm going to set mine to 18 so that you can see it clearly. You can set your editor font size to whatever you want. It's up to you. The general structure inside of a LaTeX document consists of 2 parts. The part up at the top is called a preamble, and the part down at the bottom is called the body. The preamble, which by the way, if you need a comment in LaTeX, you can put a percentage sign in there, just like you can in MATLAB. The preamble up at the top sets what the document looks like, whereas the body down at the bottom sets the content of the doc. This part, the preamble, at least in 176, is given. So you're not going to have to worry too much about how do we provide the settings inside of a preamble to get the report to look the way that you want. We're going to build up some basic behavior inside of the preamble, just so you see how it functions. And then I've commented up the template for 176. So if you want to know exactly why we're loading something somewhere, by all means, check out the template, and you'll be able to kind of hack your way through and see what's going where. And then you'd have to refer to the documentation of an individual thing in order to learn exactly why I set something the way that I did, or it was set the way that it was. The minimum amount that you need for a document inside of LaTeX is a preamble that says, what kind of document do I want? and a little bit of text in the body of your document. So to tell LaTeX what kind of document you want, you specify the class by saying /document class. The slash, which I think is called a backslash, not a forward slash, the backslash in LaTeX is a reserved character. That means the next thing that follows this is called a function, right? It's the name of a function. Here, the name of the function is document class. Input arguments to functions are given with curly braces. Input equals curly brace. The type of document class that we would like in most cases where you're not like writing a book or a poster or something is called an article. That's a generic, like, I don't know, up to 20, 30 pages or something like that. We would call that an article. If someday you want to publish a book, you change document class to book and you get a whole nother set of functions and typesetting options that you can use for a book or a poster or a presentation. You can make slides with LaTeX. All of that works fine. But we just want an article. In order to set the body, we have to introduce the first sort of, well, I don't know, this is like the third major concept behind preamble and body and function is an environment. So environments in LaTeX are ways of saying everything between a begin and an end statement should be understood as a particular type of material. This type of material is the entire document, right? We say begin document and end document. So what we have written here is the document environment, right? And specifically, that's the start of the document. Generally, nothing goes below end document. You can put comments down there, but I'm not aware of a way to put code down there and have it run. I think the end of document is the end of your document. That's the last thing that runs. And so, like any programming language, if we wanted to start off with a hello world example, we would throw hello world in there and hit recompile and see what we get out the other side. And there we go. We have hello world out the other side. If you want to enhance the features of LaTeX, the core features of LaTeX are usually good enough for most basic documents. But particularly within STEM, there are a lot of packages that can help you do fancy things in STEM that look really nice, that are kind of hard to do if you had to sort of hack your way through it. Before we get to some of the, well, actually, let's start with one of them. The most sort of generic one that doesn't really contribute to a final document at all is called a lipsum package. So in order to add an additional package that sort of enhances the features of LaTeX, all of which are free, by the way, you don't ever pay for a LaTeX package because they're free. You can say /use package up in the preamble. And then you specify the name of the package that you want. If you've ever looked at the, like trying to lay out a website, you've probably seen some sort of space-filling Latin text that doesn't really mean anything. It's just there to show you what the layout looks like. That text is called lipsum or lorem ipsum text, and there's a package that allows us to generate that text called lipsum. It stands for lorem ipsum text generator. Right? It'll allow us to generate blocks of text just so that we can see what it looks like over in the document. So loading the lipsum package like that then gives us the ability to use a function along the lines of, say, yeah, here's fine. Lipsum, just lipsum, right? Let's not give it an input argument right now. If we do that, then we get a ton more text, right? But it's all this sort of weird Latin. It is actually a book somewhere. I don't remember what the actual book is. It's like a letter from somebody to somebody. I don't remember. At any rate, it's just a bunch of space-filling text so that we can see what the document looks like. For example, if you zoom out a little bit, you'll see that the margins are kind of weird, right? They're a little bit bigger than we would typically expect a margin to be. The reason for that is because the default margins that are set on here, we're expecting you to cut the edges of this book, right? If that were printed out, the text would be about this big. It would look kind of like a book that you would read. Most of the time we don't want that, and so we can use other packages to adjust the behavior, right? We're adjusting, or I shouldn't say the behavior, we're adjusting what the document looks like. And so those are going to go up in the preamble because that's where that stuff goes. So for example, if we wanted to change the geometric features of our package, right, or of our document, right? How far left does it go? How far right? There's a package called geometry, which is pretty much the go-to package anytime you need to adjust that kind of stuff. And specifically, we would like to set the margins to be something a little bit more common that we're used to seeing. For example, 1 inch. We can provide an optional input argument with brackets. So brackets equals an optional input argument. So I've got the use geometry, or use package, and we said we wanted to use geometry. This one uses curly braces, and then we gave it an optional input argument here of 1in, which stands for 1 inch. You could do like 2 centimeters if you want, as like 2 cm, and that would be fine. It would work the same way. But those square brackets that you see there, those are the optional input arguments. So some functions have them, some functions don't. Another function that has them is the lip sum function that we were using down here. Maybe we don't want all of that lip sum. Maybe we just want the first 2 paragraphs. So we can say lip sum 1-2, and that will give us 2 paragraphs of space-filling text. Oops, I have an argument on here. Let's just do lip sum 2. Pretty sure that was what my mistake was. We'll just say lip sum 2. There we go. Oh, wait. Oh, I forgot to say margin. That's what it was. It's not 1 inch. It's margin equal 1 inch. Geometry was smart enough to figure out what we wanted. When it saw 1 inch, it was like, you probably want the margin, and it reset it. But I forgot to type margin is equal to 1 inch. That's how we tell geometry that what we would like is a margin with 1 inch. That's how it goes sometimes. And now we cut our lip sum down to just the second paragraph of lip sum. We can set that to any number that we want. We could say something like 1 to 3, which is what I'm going to do just so that we can see a little bit of text on here. The other thing I'm going to do, which you can do or not, it's up to you. It might be easier for you to see it this way on your document. But I would like you on this stream to actually be able to see what we're typing over here. So I don't like a narrow margin over there. I like a bigger margin so that I can zoom in and it kind of looks comfortable. So I'm going to comment out the geometry package so that I get those weird fat or margins around the outside edge because now I can zoom in on it and you can see a little bit more easily what we're actually typing. Most documents use margins setting on LaTeX, so when you go to create your own, you can use geometry. And you'll see that it gets used on the template as well. Some features of LaTeX, like I said, are baked in. Some need packages. So an example of the baked-in type functions that are already inside of LaTeX, if you want to create a section header, there's a command called section. So for example, in your reports, you need things like intros and backgrounds and theories and that kind of stuff. So you might say that this is section introduction. And then maybe you come down a little bit further and say section background, and then section conclusions, something like that. Notice the way that I gave the function is a what do I want, right? It doesn't actually typeset it over here in the source code. It's saying, this is what I want you to do. So what I would like you to do, the way to interpret this command, is I would like you to create a section header, and I would like you to put the text called introduction inside of it. LaTeX then took that and during the compilation process turned it into this. It said, all right, you want a section header, it's going to be a little bit bigger than everything else. It's going to be bold. It's going to be offset this way a little bit. And fairly importantly, it's going to get a number. I did not tell LaTeX that the first section is 1. It is intelligent enough to know that the first section is 1. And similarly down here, when I put the background section over here, I did not say that that's the second section, and I did not say that the conclusions is the third section. And in fact, if you flip the order of those around in the source around here, the text will switch around, but the numbers will stay the same. It'll automatically renumber them correctly, which is great if you have a lot of sections or if you have like subsections or something like that. You can probably guess what the command is for a subsection. You probably said it in your head right there while I was talking. It's subsection, my first subsection. Right? And so this is a way that we can highlight the automatic numbering in LaTeX that's so useful. We're using it here as a section. We're also going to see it as like figures and tables and equations. We often want those numbered, and something that LaTeX does really well is automatically numbering. So all I did was say I want a section, and then within that section I want a subsection. And then I want to go back and go to the normal section. It knew that that means the numbering has to go 1, and then the next one is 1.1. And also notice this is a little bit smaller than introduction, right? That text is a little bit smaller so that visually it's distinct from a section header. And then it encountered the next section header and it went back to the way that it originally was going to. So that's some of the auto numbering and some of the auto formatting features that are in LaTeX that make it useful. And we'll touch on a few more of those as we go. But those were baked in functions. There's a couple more functions that we use a lot within STEM that I want to show you now how to use. First, we need to load the appropriate packages. So we're going to load a few of them. I'll just describe what they do, and we'll check out the documentation for some of them. One of them is math, right? In STEM, we want to do a lot of math often. The American Mathematical Society has its own LaTeX package that says this is what it ought to look like. And so we can load that as AMS Math. Chemistry, I'm not familiar with a particular governing body that says this is the way it's supposed to look like and therefore everybody does it. But there is a standard that everybody seems to use, which is MHChem. So MHChem allows you to typeset chemical formulas. I believe the MH in MHChem is just the name of the author that created that package. So I don't think it stands for anything in particular. We do want units a lot. So we have SI Unit X. There is an old package called SI Unit. There's sort of a naming convention in LaTeX of there might be an existing package, and then if we want to add an extension to it, we put an X after it. So SI Unit X is an extension of the original SI Unit package. So that'll allow us to typeset numbers. The last two that we want, there's a physics package, which allows us to typeset things that often show up in physics, like differentials and operators and vector notation and that kind of stuff. And then last, if we want graphics, there's the GraphicX package. So that's like if we wanted to add figures into our document. Your template inside 176 has way more packages than that and way more functionality, all of which is described in the actual document, in the compiled document of the template. That will tell you how do I use this template. So we're going to start with these and illustrate some of their examples so you get a flavor for how LaTeX works. Before we do that, though, we're at about the halfway point. I'm going to pause here for a minute just so A, I can have a little bit of tea, but also B, this is the base where I want to go from moving forward. So if you can't get your document to compile like this, you can throw some questions over into chat, but I want to give you a moment to catch up here because everything that we're going to do assumes that this is already working, and we're going to modify this as we go. So I'm just going to wait here until maybe like 2:36, 37, something like that. If you have any questions, you can throw them over in the Zoom chat. Otherwise, just relax for a couple of minutes, and we'll start up here again in 2-3 minutes. Okay, so I'll assume that you're up to about this point, and then we're going to keep going from here. So the first thing I'm going to do is rename these sections to illustrate the things that we want to do. The first thing that we're going to do is math. The second thing that we're going to do is chemistry. And the third thing that we're going to do is numbers with units. So I'm going to get rid of the stuff in between here and just organize this so that we can see what's coming next. In order to typeset stuff in math, like I said before, that's one of the things that LaTeX is really good at. In fact, the original core unit, the tech part, that was designed as a math engine to typeset math very neatly. If you dig into Word, you'll actually see the advanced math editing window in Word is just a LaTeX environment. Same thing. I don't think you've ever edited stuff in Canvas before, but if you have, the advanced math editor inside of Canvas is LaTeX. I don't know if I would call it advanced or not. I think it's a more direct way to tell the computer where does stuff go. If you've ever had to create a fraction and then the thing on the top has both a subscript and a superscript, it's really hard to paint or pick the correct portion inside of Word to get that to write correctly. So as an example, let's say that we wanted to write a conservation of mass expression. So we could say a conservation of mass expression is something, and then we're going to start writing some stuff in here. The way to start writing math in an environment is to begin an environment called an equation. Math in LaTeX is generally inside of an equation, although we will see options of how to do that later that don't involve begin equation, end equation. So this is an equation environment. And if we wanted to start with a basic conservation of mass style expression, maybe we want a fraction that says dm dt is equal to mass in minus mass out, right? And then we'll kind of build up as we go from there. To create a fraction in LaTeX is /frac, and then the first argument's the numerator and the second is the denominator. So maybe we say dm dt, and that's equal to m sub in minus m sub out. That's got the concept of what we want, right? If we compile that, though, we're going to see a fair number of problems. Some of them are more obvious than others. It sort of depends on how familiar you are with what it ought to look like. The first thing that I'll note is, what did it get right? What did LaTeX do correctly? Well, the first thing that it did correctly is this kind of looks like an expression, right? The typeface is changed a little bit. It's centered, so there's some space over on this side and there's space over on this side. There's some space between the previous sentence and this sentence, and there'll be more space below it before you get to the next one. It did that correct. It also correctly added a number on here, right? I didn't have to say that there was a number. I didn't have to say that it was supposed to be in parentheses or that it was supposed to be over on sort of the right-hand side, close to the margin, but not quite at the margin, blah, blah, blah. It did all of that correctly. A little bit of what it didn't do correctly is if we zoom in a little bit on the equation, you'll see that in and out are not typeset correctly. Let me drag that up to here where you can see it. So this was supposed to read something like m sub in, but instead we got the m is okay, the I is okay, but the n is wrong. The n is up on the wrong spot, and similarly the ut over here on out is in the wrong spot. This was supposed to read as something like m sub out. So in order to correct that, we have to start building up our mathematical expression inside of LaTeX with braces. That's usually what we have to do when we want something beyond a fairly straightforward expression. There tends to be a lot of braces inside of there. So we capture the in within a brace and the out within a brace. And so if we recompile that, what you'll see is that now this is indeed m sub in and this is indeed m sub out. Right? They are properly subscripted, and that's because this phrase sub out is within a brace, right? It says everything that follows this brace, that's enclosed by this brace, is supposed to be a subscript. If you wanted a superscript, you would use a caret in exactly the same functionality. The other features that are on here that it did wrong may not be as obvious to you. And that's okay. They may simply not be obvious to you because you like it the way that it looks like that, which is fine. There's nothing wrong with the way that this looks. It can become a little bit more of a problem if you would like, for example, that subscript to not be a symbol but an actual phrase. So maybe instead of out, you would like to say out of CV, right? Like out of a control volume. If you recompile that, you get a weird looking sort of smorgasbord of stuff that came out over here, right? It interpreted that as math. It thought out of CV meant you want the symbol, the mathematical symbol O, and then the math symbol U, and the math symbol T, etc., and gave you exactly that, because whether you know it or not, that's exactly what it asked for. So if you ever have to escape out of something like that, you can add extra commands like text to get actual text to show up. So for example, if I said /text out of CV, now when I recompile that and I look over at the m sub out, it actually looks like m sub and then a phrase that's just written as text. And that comes up a fair amount when we're, doing a derivation or something like that. It sort of depends a little bit on your own sense of style, whether you would like m sub in to be in like we have it here, or if you want it to actually look like text. It just depends on what you prefer. But there are cases where, sorry, your preference is wrong. If you say m sub out of CV and it's all typeset as math, that's a mistake. It's okay. It happens. I made a mistake over in Zoom chat. It happens to everybody. The difference is you get graded for it and I don't. So, apples to oranges. The other thing that's weird, and this is only an example of how to sort of use documentation, this is not actually how differentials are supposed to be typeset. The D that sits on here, that's actually an operator. It's not a variable. And the way that it's being typeset right now is as an operator, or is as a variable. And it's supposed to be typeset as an operator. This I'm using as an example to show you how to find documentation. The physics package has a way of typesetting derivatives with much less effort than frac_d. Or if you wanted to get the way that it's supposed to look like, it's actually supposed to be /textd on both of those. But it's really annoying to write /textd every time that you want that. That's actually the way that a derivative is supposed to look. If you look back through your textbooks, you'll see them written that way. And where you don't, you'll grit your teeth a little bit because you'll say, oh, you guys screwed that up. We can do this a lot more easily in LaTeX because we have the physics package. So anytime you want more information about how to use a particular package, my suggestion is Bing the package. So say LaTeX physics package. What you're looking for is a documentation file. So it should be a PDF. You don't want to look at something else. So I'm looking at a PDF here, and you want it to be coming from a link called CTAN, which is the Comprehensive Tech Archive Network. That's where all of these platforms go to grab the packages, and so those are kept up to date pretty well. So you want to make sure you're reading the documentation from CTAN, because if you're not, you might be reading old documentation, and you can do exactly what you're supposed to do, and it'll mess up because it's an older version. So let's check out the physics package, and I'm going to assume that you have read the entire documentation in the fraction of a second it requires for me to scroll down through here. But right away in the list of commands, which most small packages like this will give you a list of commands, you'll see they have the ability to write a derivative. You can also write vectors and bracing and operators and stuff like that. It has an ability to write matrices very nicely. But if you click on derivatives, it'll take you down here and show you this is how you can write a derivative. So if you want to typeset a differential equation, you can use one like this, where it's an input argument. It actually looks very similar to the fraction command. You say /dv, you say what you want on the top, and then what you want on the bottom, and it will typeset it as the appropriate thing that you want. And then it's showing you all of the other variations that you can have on a derivative. The only reason that I did that, it's perfectly fine if you want to write a plain old D instead of a derivative D. They are different, but the reason I say that is to point out CTAN, which is the Comprehensive Tech Archive Network. You may even find some packages written by certain faculty instructors that may be teaching you. So if I wanted to do that here, I would say something like dv with an M, and then DV with a T, or with a T as the second one. That is a shorthand way of doing the same thing. It actually messes with the spacing a little bit too, which is harder to see, but that's how you can get a derivative to show up. If you want to do more stuff, additional math operations are fairly straightforward. There are lots of good tutorials. So if you ask Bing to show you some results for Overleaf Introduction to Math, it'll go through all of the very common ways that we might have to typeset math. But that's an example of something that you might have to do. If you wanted to add, for example, a dot to the M, you could say /dot and put that around the M, and now you'll get a little dot that represents like a mass flow rate or something like that. All that is probably on the very first page of any kind of a tutorial that you have for LaTeX math typesetting, the majority of which you'll cover in probably 5 minutes, right? Fractions and parentheses and subscripts and superscripts handle an awful lot of math that you might need. There is another way to typeset math that's slightly different. It's a little bit faster, but it does something different. So if, for example, we wanted to continue this with maybe not a conservation of mass expression, but, I don't know, and a version of the Pythagorean, what's that called? Pythagorean theorem. I was blanking on it. Is the other way to do math, and you can type whatever text that you want right there, is with a slash operator and then a square bracket. So if you say slash open square and slash closed square, that will set an environment that looks very similar to math. And so we might say something like L is equal to square root of maybe a squared plus b squared. And then recompile that. There's a question over in chat. My cursor on Overleaf set as a horizontal blinking line instead of a vertical line. I believe you have hit the insert key on your keyboard, which means if you start typing, it'll overwrite what's already there. So hit insert, and it should switch it back to a vertical cursor. So when I use the square that's on here, I get a couple of different things. So let's highlight the differences in the brackets. So what I did was I used a bracket here and a bracket here, a square bracket. The math that's inside of there is the same, right? This part here is the same. It still looks like math, which is what we want. The only difference is we don't have a number anymore. And so if you need an equation that doesn't have a number, chances are it's like part of a derivation or something. You're not going to refer to that number anywhere else in your document. That's about the only place that is used. It's important enough to show how we're reasoning something out, but it's not important enough that we're going to refer to it later. And so you can use the square brackets to get an equation without math. Or, yes, sorry. You can get an equation without a number. It's still math. The last way that we use math is really more of a communication issue. So most people would be able to reason out what you mean. So for example, in this Pythagorean theorem expression that we have here, we might say something like where A is the, width, and B is the height. Most people would be able to figure out when they see an expression like this that those two A's are the same. Right? The A that you've got here is the same as the A that you've got here, which means the A that you've got in this math environment over here is the same as the A that you put in the text. But if you look at it for more than a moment, you'll notice those two A's are not the same, right? This one is italicized like math, whereas this one is not. If it's A and B, it's probably not the end of the world, right? Most people will figure it out. But that does become a problem. For example, in the Reynolds number, do you mean the Reynolds number or do you mean the real part of an imaginary expression? Those can show up in the same location. Another one that shows up a lot is L. Do you mean L? Do you mean a script L? Do you mean maybe in a capital I? Do you mean the number 1? What do you mean? It's important to get those the same. If you've ever come across a textbook that had a typo in a math equation, it is a massive pain in the neck to try to figure out what the author actually meant. You got to jump through a bunch of hoops to try to figure out if they even made a mistake. So it is important to get those two things to be the same. It's a question of communication. It's a question of clearly communicating your idea to the reader. And so the way to do that is to use what's called an inline math environment, which is to put a $sign on either side. So if you put a $sign on either side and then recompile it, you'll get what we call inline math, right? So this, the $sign that we've got here, that denotes inline math. And now you can see that the A that we've got here is indeed typeset the same way as the A that we have up here. And similarly, B is the same as the B that we've got up here because we captured both of them inside of a $sign on either side. That's kind of important because once you start writing reports, you'll want to refer to variables, densities and distances and Reynolds numbers and stuff like that. It is important that those look the same because it is a question of communication, and so it's being looked for. Hint, hint. So those are all the major ideas of math. Like I said before, being something like LaTeX typeset math to get tutorials. You shouldn't need very many tutorials. It'll probably be whoever's writing the theory that needs the first tutorial, and maybe the results and discussion folks will need a tutorial on how to typeset math. But a little summary table somewhere of how to make the most, 10 most common symbols in math, that's going to wipe out pretty much everything that you need to use. We're going to do the one other one here, which is chemistry, but that should take care of most of what you need. Fractions, parentheses, superscripts, subscripts, that kind of stuff. I think you'll pick up on it pretty quickly as we go. The other thing that we need a lot, at least in chemical engineering, as well as probably chemistry, are chemical formulas. So if we wanted to say something like the chemical formula for water is H2O, and for methane is CH4. If I compile it that way, it's just going to look exactly like that, right? It looks like an uppercase H and then the number 2 and then O. We've already loaded the function mhchem, which allows us to typeset chemical formula. And we do it in a way similar to the way that we've used like square roots or texts or dots or something like that. We wrap the thing that we want to be represented as a chemical formula in curly braces, and we say apply the function CE to that. So we say /CE H2O, and we say /CE CH4. That will automatically typeset chemical formula in the way that we're after, right? So if you look over here, CH4 is now CH and then a subscript 4, even though all we wrote over here was just CH4. The chemical equation package, or the MHChem package, knew that what you probably want is a C followed by an H followed by a subscript 4. And you can add complications to this to see how MHChem behaves. If you need like electron symbols, like the little dot for a radical or a plus or something like that, or a charge symbol, you'll have to check the MHChem documentation. And right up at the top is a list of like 15 of the most common chemical formula that you would need. And then the more rare ones are a little bit below that. So you can add that down there too. So maybe you don't want methane, but you want, I don't know, what's ethane? Ethane is C2, and then what, H6 is methane? Because I would complete it. So you can just write C2H6, and it will automatically typeset that as C2H6. You can also add those into your math expressions, right? So you can say something like the density of water is denoted as, say, rho and then sub/CeH2O. Right, so you can include chemistry inside of math formulas or formulae, and you will get it just the way that you want it. But it takes a little bit of getting used to, right? This may not have been the first thing that occurred to you when you said, in my mind, I want density of water, rho subscript brace /CE brace H2O brace $. is probably not the first thing that pops into your mind. But as you work with LaTeX a little bit more, you'll be able to assemble these parts a little bit more easily as you go. So that's chemistry. You can put those in captions, you can put them in math, you can put them all by themselves. You can write chemical equations. So for example, if you want an unlisted chemical equation, you could say something like /CE and say H2 plus O2 goes back and forth to what? H2O. I didn't balance that correctly. We can go ahead and balance that. This would be 1/2 H2O. Could use something like that, right? And you get a nice chemical formula that's typeset the way that you would expect it to be, and there it goes, right? It's a nice way to write chemical reactions as well. Oh, the head's in the way of where I compiled it. Thank you. There's where we compiled it. So this was the row H2O. This part, that's what we had accomplished with this. And then a chemical equation or a chemical reaction written all by itself, you start off with a math environment like what we've got here, and then inside of it you would say /CE, and you can write out the symbols that you need. It will know, for example, that the 1/2 that sits in front of here, that's a stoichiometric coefficient, right? So it shouldn't look like 1/2, it should look like a fraction 1/2. The CE package already knows that. Last thing is numbers with units. So we can actually combine all of these to show you what that combination would look like. Numbers with units, as an example, might be something like the density of water is 998 kilograms per cubic meter, 3m, cubic meter, something like that. If I compile it, it's not that somebody wouldn't know what that means, right? They will get the idea of a kilogram /m3, that means kilograms per cubic meter, which is what you wrote here. It does get a little bit more confusing the more units that you have in a system, and we've already loaded a package called the SI Unit X package that's really good at typesetting units. It will get it right pretty much the first time, every time, and eventually you'll probably get used to it enough that you'll get a little bit frustrated when you have to come in here and do something like, I would like that to actually be superscripted, and then it doesn't work the way that you want, or it doesn't look quite right every single time. In this case, the caret didn't do anything at all. So instead of that, we have the SI Unit X package. And the SI Unit X package gives us the SI function, where the first argument is the number, and the second is a set of commands that represent the unit that you want. So if I want kilogram per cubic meter, somewhat not surprisingly, I write /kilogram per cubic meter. Right? That's pretty human readable. It's pretty obvious if it doesn't show up the way that I want. I must have messed up with like kilogram or per cubic or meter or something like that. And it will automatically get all of the spacing correct. So it puts the space in here where there is supposed to be a space. It gets the spacing between the kilograms and the meters, and it raises it to a -3, which is the default SI notation. But if you prefer something that looks more like kilogram per cubic meter, that is an option inside of SI Unit X. Please don't change that in your template. It's just kind of a heads up in case you want it. It is possible to write it that way. There's also a shortcut, so you don't have to write out kilogram every single time. So for the most common base units, you can write something like per kg and per m, and that means the same thing, right? So you can get it to, once you're familiar with those commands, and it doesn't take very long because they're labeled in a fairly obvious way, it's much faster to write /kg per cubic meter than it is to put kg and then space m and then -3 and then highlight it and say superscript, especially when that compounds up a little bit more into a more complicated system of units. Sometimes we don't want the number and we just want the unit, and that's the last thing that I'll mention for the SI system is sometimes we might want to say something like the units of density are kilograms per something, something, something. That works almost the same way, except you use lowercase si and you don't give it a number. So you would say something like kilogram per cubic meter. But it's with a lowercase si. So the difference between the two that we've got here is there's a number when I want a number, and there's a capital SI versus a lowercase si, and then there's no number that sits in front of it. And that gives us the ability to just write units by themselves. Maybe you want to say the units of rho are kilograms per cubic meter, or the units of L are length, or something like that. The lowercase si function gives us the ability to write those. So those are the last of the three sort of STEM features that I want to cover. We're briefly going to go over how to put a figure in here, and then we're going to look at the template for your reports. And that will show us how we can do what's called a cross-reference as well as a citation. And those are usually only used by the folks who need them. So people like in theory will generate a bunch of equations that you'll want to label, and then the people in results will need them. And there's an example of how to do that in the template. But let's put a figure in here. So section, my first figure. The first thing you need with a figure is an actual file, a figure file. There are various ways to export high-quality figures out of MATLAB, which I believe are summarized on the website, or on our course website, so please go check that out so your figures are legible and readable. We don't have enough time for that right now, so we're just going to find a picture. If you've never seen a C sheet before, congratulations, you're one of today's 10,000. This is a C sheet. It is adorable, and that is not an opinion, that's a fact. So I have a C sheet here. I'm going to save that as an image. Make sure you save the image as a standard style image, like a JPEG or a PNG or something like that. So I'm actually going to kind of cheat here and take a screenshot to make sure that I can save this thing as a PNG, because that's the file type that I'm most familiar with. So I'm going to throw it into Paint. Sheet. But you can get basically any file that you want. If it's a PNG or a JPEG or a bitmap or something like that, all of that will work fine. Any old image works fine. How do you start a new paragraph? Add extra white space. This is a new paragraph. To create a figure, we first have to upload the figure. This is the first time that we're going to look over here at the file browser. So as I said earlier, there's a button up here at the top that says Upload. That's how we upload a file. So we click Upload, and then we go find our sheep. So here's my sheep. So now I have sheep.png in here. If I click on sheep.png, you should get a preview. If you don't get a preview, something probably went wrong. You should get a preview of your C sheep, or whatever it is that you're uploading. To put that into our document, we need a new environment called a figure environment. So in order to create this, use a figure environment like this. We're going to say begin figure, close it with an end figure. And there's a couple of things that are standard to a figure. The first thing is that they're centered. So there's a function called /centering, which will keep your figure centered. This, by the way, is the template covers all of this, so you don't have to memorize this particular layout. Then you have to put the actual graphic in there. So we're going to say include graphic, and I'm going to say sheep.png. I never remember if it's graphic or graphics. We'll find out here in a minute. And figures always have captions. So we'll say /caption. This is a C sheep, right? And that'll be our caption. So this is our figure environment. And if we compile this, like I said, I never remember if it's include graphic or graphics. Evidently it's graphic, plural. So I'll put an S on there. We should get a massive sheep over on our page. So I'll zoom out, and I'll look down, and there's our sheep. It's there, right? We've got roughly what we want, but that is obviously not where we want that image located. We also don't want it sort of shoved way over to the side or anything like that. Your image may be even larger. It could be off the page. That's okay. The graphics package gives you an easy way to adjust the size. Most commonly what I would do is set either the width or the height and then allow the graphics package to keep the scaling the same and set the other one. So for example, let's say that I want the height here to be 1.5 inches. I would include that as an optional input argument to include graphics. And now it will resize my image, and it moved it up here so that I have a nice little C sheet. Right, it set the height to 1.5. It left the width whatever it needs to be, so that it will fit on whatever aspect ratio is that we need. Notice one thing that happened that my guess is every time you see for a while is really going to frustrate you, and you're going to be like, LaTeX, you are so dumb. Why do you keep doing this? The figure environment is at the bottom of your text. It could be anywhere in your text. It doesn't matter. But the actual figure here is located at the top of the screen. That is not an accident. That is LaTeX using its built-in rules for what a neatly typeset document typically looks like. Those rules are best summarized this way. The only place that a figure ever goes is at the top or the bottom of a page. A figure should almost never go in the middle of a page. Crack open any textbook you have laying around, find a figure in the middle. It's very rare. It may be there. There could be a good reason for a figure to be in the middle. It is extremely rare for a figure to be in the middle. So for the most part, you can let LaTeX dictate where your figures are placed. The placement will generally improve the more text you add to it. So if you add the figure first and you've just got a bunch of empty section headings, it's going to look kind of messy. But if your intro is a page and a half, it will be able to neatly place that figure near the bottom of the page. And you can move the figure environment a little bit back and forth in your text and kind of play around with it and see where it goes. Generally, the only thing you should need to do, though, is force the figure to the top or the bottom of the page. And so you can force it to the bottom with a B command. So if you say square bracket B after the figure, it'll force it to go to the bottom. If you really want LaTeX to know that you mean business, you can put an exclamation point after it, and it will try even harder to do what you're asking. It may still fail, and usually it'll fail if it's a very unusual document, right? If you got like lots and lots of figures or something like that, it's going to have trouble organizing those. Actually, the same way that Word would have trouble organizing them. If you find yourself ever at a time where you have figure followed by another figure, it's probably the case that you need to rethink the way that you're presenting information and maybe put those two figures next to each other, or maybe even combine that information onto a single plot. It's pretty rare that we ever need a figure followed by a figure, and it's basically considered a faux pas, or in other words, a no-no, to have a figure and then a third figure under that. That's called a figure dump. Nobody likes figure dumps. So if you need more than one in a row, think really hard about what you're doing. You may want to restructure the actual figure itself so that they're maybe side by side or something like that, which you'd have to come up with a way to modify their appearance, like a paint or something like that. There are ways to put figures side by side in LaTeX, but they're a little bit more complicated than what we want to go into right now. The reason being, this completes the sort of template, or I don't want to say template, the example that we did to show you what LaTeX feels like, right? What are the general ideas of LaTeX? It's text, environments, and functions. And those combinations give you the type of output that you want, or very close to it. There may be some things that you may not be able to control quite as well, but they ought to get you close. In order to get you the report that you need for 176, the vast majority of that typesetting has already been achieved for you, and it's over on the website. So if you go to the bottom of the written report on here, there is a 176 report template, which is going to need a couple of updates. So you can grab it now, but it's going to be updated in a little while. But if you click on that, it will give you a zip file that'll contain all of these sections. So download this as a zip file. And if you would prefer not to follow along here, Professor Opakowitz says it's already updated, so this should be updated already. But if you don't want to follow along, at least watch along, because I'm going to click a fair amount here. I'd rather you see what I'm doing rather than get behind. So I've downloaded it. I'm actually going to create an entirely new project. I don't want to use this one anymore. So I'm going to go back to the main page and click New Project and upload one rather than something else. And then I'm going to scooch through here, date modified. I'm going to grab the most recent one and upload the entire zip document into this Overleaf project. What you'll see here, the first thing you'll notice is over in the outline section, there's a lot more stuff over there, right? There's a lot more files, but main.tech is still over here, and it looks similar, right? There's still a document class. I input a file here, and then there's a begin document, and you scroll down, and there's an end document. So it's still all kind of there. The things that are here that are not in the other one are obviously all of these additional tech files, but they're fairly self-explanatory, right? You put your appendix in your appendix, you put your background in your background, et cetera, et cetera. You can just delete whatever's there. The actual compiled document that you can read about does have some interesting content in it that you might want to review. This content, for the most part, is telling you how to use LaTeX for various things. It's not telling you what's supposed to go into that particular section. So if you want to know what goes into the introduction, come over to our website, and we've got a section for what goes into the introduction. If you want to know some of the tools in LaTeX that you might need for the introduction, that's what's being covered here in the template, and that's what's being covered in the other sections as well. They're generally the tools that you will need in those sections. So as you scroll down, you'll see things like citations. It's talking about math symbols in here. It'll get down to chemistry, et cetera, as we go. What I would like to note are two things, a cross-reference and a citation. A cross-reference says, I would like you to go look at some other part of this document, but wherever that is, it's contained within the document. The way to do that is if you look at a figure, for example, over here in the results section, we should have a figure. Where did my figure go? Here it is. Begin figure and end figure. This has all of the features that we just saw in our example. It's got centering, it's got include graphics, it's got a caption. It has one more, which is a label. So you can use labels to label figures, equations, and tables, and really anything else that you want, like sections, so that you can create text that reads along the lines of, equation 3 is the derivation of conservation of mass. Don't write that. That is very clunky. Or see figure 5 for a C sheep, or something like that. You don't want those numbers to be out of place because that's going to point the reader in a different direction. So again, it's not just a tool for making it look neat because we're nitpicky. It's a tool that makes it look right for proper communication. Written communication and oral communication are obviously big parts of CENG 176. The ability to label and then cross-reference something is an ability to improve your communication. Once you have something labeled, then wherever you want that cross-reference to show up, you say /cref. It stands for actually clever ref, not cross-reference, but that will put the text where you want it. And there are examples of that inside of the report template that you've got here. Like I said, that'll primarily come up, at least cross-referencing figures will come up for folks that are writing sort of results, discussion, and conclusions. It may come up a little bit above that. More likely, the folks up in the theory will have to cross-reference equations. And then folks in results will have to make use of those equations through more cross-referencing. So it is something that you'll want to check out in here in the template. But that's the link, right? You put a label where you want the label, and then whatever you want to refer to that label, you use /cref. Similarly, your bibliographies, I think you'll actually like the bibliographies. If you've ever had to write a bibliography for some other class where they make you follow a particular formatting style, it's kind of a pain in the neck. If you scroll down to the bibliography in the template, there's an awful lot of formatting down here that is annoying to do on your own. So if you take the journal example, like this 5th one, I got to make that italics, right? And then I got to put a period, or maybe there's not a period, or then there's bold, and then there's a comma after it, and then italics, and then numbers with a dash, and then a period, and then a comma. the authors are last name, comma, first name with a dot, but not when you have multiple authors, blah, 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 blah. Typesetting citations are an enormous pain, but LaTeX will do that for you automatically. All you have to do is give it the right information. So you are still responsible for a bare minimum, right? You do have to give it the correct information. The style for that correct information is over here in reflist.bib. So you can scroll down and get an idea for what these formats look like. There's book collections, which are these in collections. There are just straight up books if you need to do one of those. Journal articles is a very common one. It's pretty rare in 176 that you cite a website, but I did include it in case you need it. But it's pretty uncommon to cite a website. But the three major ones, books, edited books, and articles, you can copy paste the formatting that we have here, and that's how you enter the information. So enter the information in the way that it's given here, and do it exactly the way that it is. So for example, I have J.D. Cedar, followed by the word and. And is actually a keyword. Don't replace this with a comma. If you say comma, things are going to screw up. It has to be the keyword and. So follow that as closely as you can. Then when you want to actually use one of them, the function that you're going to use is called autocite. And so if we come over to introduction and we search for autocite, you'll find a couple of examples of autocite like this one. You give /autocite, and then you give the tag that you want that represents, actually the label that represents the citation information that you had before. So you can see up above here, I've got autocite, Perry's Buck Pie, and then Perry Batch Dist, because I'm referencing different areas of Perry's Handbook. And that will automatically typeset everything that you need. It'll automatically get the numbering correct as long as you've input the information correct. It's not that it can come out wrong. It's that if you put the information in correctly, it will come out with the correct typesetting style. It will also add, and this is fairly hard to do unless you are using autocite, and it's one of the ways that we know you're not using autocite when you should be. The superscript numbers on here are actually hyperlinks. So if you where the citation appears, it'll automatically get a superscript number. And if you click on it, it will take you down to the bibliography to that particular entry. So it's one of the ways that we figure out whether or not it's being done correctly. But that brings us right up to 320. So please do download the template and look through there for a couple of features like this citation and cross-referencing. Most of the other stuff will look similar from what we did in class today. So I'm going to wrap up the formal lecture here. I will stick around a couple of minutes in case you've got any questions over in chat. But it was great to see you again. I hope that we will get to see each other in person sometime before everybody graduates. Fingers crossed. Have a great day. Stay safe out there. I'll stick around over in Canvas chat for a little bit if anybody's got any other questions. Have a good one all. You're very welcome. How do we get the report template file on Overleaf? It's a two-step process. So the first thing is go to the website, go to the written communication page, and all the way down here at the bottom is a template.zip. So download that, and then when you're over in Overleaf, you'll have to go up a little bit and then create a new project and say upload project, and you'll be able to drop the zip file into there, and it will auto-populate all of that stuff for you. I wouldn't put it into an existing project because something might have the same name and it might screw up the naming on there. Your code seems to crash when you type something for height. The best I can do is probably go into the example that we've got here. And just sort of leave it highlighted on the height part here and just try to do like a one-to-one comparison here and see where you've got yours different. Potentially the other place that you may have an error, it does have to be within a figure environment, so you need to begin figure and figure. Actually, it doesn't need to be in a figure. It would compile okay without that. but you might need the GraphicX package. So we also installed GraphicX up here. So you might want to pick that up as well if you don't have that installed in your preamble. But most likely the problem is somewhere here. Maybe you don't have the file uploaded. Okay, it was the package. Perfect. Perfect. I'm going to keep answering questions over in Zoom chat, but I'm going to wrap up the stream over here. So I'm still over in Zoom if you have any questions, but I'm going to wrap this particular part up so that if anybody pops in, they know we're done at this point. So have a good one all. Hopefully we'll see you soon. Good luck with everything and stay safe out there.